Controlled Environment Plant Production Engineering Technology Education modules are developed and presented by The Ohio State University, Rutgers, and the University of Arizona with support from USDA and NIFA through their Higher Education Challenge Grant Program. In this module, we will discuss about natural ventilation process in greenhouse systems. This module is presented by Dr. Murat Kasira of the University of Arizona and Dr. A.J. Boat of Rutgers. By the end of this module, you will be familiar with natural ventilation process in greenhouse systems, the main factors affecting natural ventilation process, and we are also going to look at advantages and disadvantages of natural ventilation. Greenhouse ventilation is an exchange process of air between the inside and outside of the greenhouse system. The purpose of ventilation is to control temperature, humidity in the greenhouse system, and also to supply carbon dioxide from outside air and to reduce the thermal stress on workers. Typical methods to prevent the excessive temperature rises in greenhouse systems are ventilation and cooling. Ventilation can be achieved by using mechanical ventilation with fans on the greenhouse, or by natural ventilation using roof and side vents. Some of the common cooling methods used are evaporative cooling systems, such as with pad and fan use, or high pressure fogging systems, and low pressure misting systems, which are mostly used for propagation houses. Shading with internal and external shade curtains are also used to decrease incoming solar radiation in greenhouse. Cooling can also be achieved by using whitewash on the greenhouse glazing. There has been considerable interest in glazing materials which can selectively reflect or absorb the infrared region of solar radiation. The efforts in advancing such covering materials have been in constant progress, and films with such properties are also commercially available. So depending on the climate, region, production system, cost factors affect selection of one or several of these methods for greenhouse ventilation and cooling. There are advantages and disadvantages of using mechanical and natural ventilation systems. Some of the advantages of mechanical ventilation system is that they are easier to design and to control, especially with the use of variable speed fans. The ventilation rates can be predictable and they are easier to measure. We can achieve high ventilation rates, and mechanical ventilation systems can be used with pad and fan evaporative cooling. Some of the disadvantages of mechanical ventilation is that they are usually located at one end of the greenhouse, so the airflow is in one direction, and these systems can lead to non-uniform conditions in the greenhouse space, and mechanical ventilation use more energy to operate. While natural ventilation systems are easier to operate, they use very low energy to open and close the vents. More uniform conditions in the greenhouse can be achieved. This system can be used with fog or misting systems using evaporative cooling, and natural ventilation is cheaper. On the other hand, the disadvantage of natural ventilation is that they are more difficult to control to achieve certain ventilation rates because we are at the mercy of outside conditions. They are difficult to predict and measure ventilation rates. The ventilation rate can be very low or very high depending on the outside climate, and the roof vents can be damaged under high wind conditions. Natural ventilation is the process of supplying and removing air through an indoor space without using mechanical systems. It refers to the flow of external air to an indoor space as a result of pressure or temperature differences. Natural ventilation is used for greenhouses and screenhouses. These systems do not require any fans to draw air through the greenhouse space. Natural ventilation works on thermal buoyancy and wind effect. Thermal buoyancy helps hot air to rise because of reduced air density. Wind effect creates pressure differences contributing to natural ventilation. Wind effects usually dominates at pressure speeds higher than 1 meter per second. Growers need to install sidewall and or roof vents to achieve proper natural ventilation rates. Natural ventilation system is not combined with evaporative cooling pads. If additional cooling is required, a fogging or misting system must be installed. There are two types of natural ventilation occurring in the greenhouse system. The first one is wind-driven or wind effect because of pressure gradients created by the external wind, or by buoyancy-driven ventilation, sometimes called chimney effect. Under buoyancy-driven conditions, the air density changes due to temperature gradients. The hot and humid air is less dense and it rises towards the roof. On the other hand, cold and dry air has more density and it sinks towards the bottom of the greenhouse. As the hot air rises towards the roof vents, it exits through roof and or side vents from the greenhouse. The main factors affecting natural ventilation process are the temperature difference between the greenhouse interior and exterior, or delta T, the relative humidity inside the greenhouse, the vertical height difference between the inlet air opening and the outlet air opening, and the total area of both the inlet and outlet openings. Finally, the pressure gradients due to wind forces. Here is an example of demonstrating the effect of height of the roof ventilator opening from floor in the greenhouse on temperature difference between the greenhouse interior and exterior. This example is from a naturally vented greenhouse without the use of side vents, and the analysis use heat balance equation for natural ventilation under a steady state condition. The analysis here assumes an internal net radiation of 600 watts per meter square, and roof ventilator to floor opening area ratio is about 20%. By looking at the data here, you can see that the temperature rise decreased as the height of the opening increased for all cases of external wind speed. When no external wind speed existed, in the case of this red line, with 0 meters per second external wind speed, an increase of 1 meter in the height yielded a reduction of approximately 0.5 degrees Celsius in the temperature rise under high solar radiation condition. While the temperature rise decreased with an increase in wind velocity, the effect of increased height of the roof openings decreased with an increase in wind velocity. This is the case with 2 meters per second in this example. The reason for this is that because the wind effect on greenhouse openings is not affected considerably by the height of roof opening, and the ventilation process is driven dominantly by the wind effect compared to ventilation caused by chimney or buoyancy effect force under range of wind velocities. This example shows that the taller height of the ventilation opening results in greater greenhouse capacity to help preventing sudden changes in greenhouse internal climate, and that improves the spatial uniformity in the greenhouse as well. Additional advantage of taller greenhouse is to promote the ventilation caused by chimney effect and the mixing of cooler incoming air through roof ventilators with internal air, because the location of roof ventilator opening is raised. This example also shows us that the height increase is effective, especially when external wind velocity is low or under stagnant air conditions. Let's look at this example on the slide to discuss about the roof ventilator opening area on temperature difference between the greenhouse interior and exterior. The example here assumes an internal net radiation of 600 watts per meter square. The height of roof ventilator opening from the floor is 4 meters, and the wind velocity outside of the greenhouse is 1 meters per second. Again, to remind that this example is from a naturally ventilated greenhouse with no side vent use. As you can see on the data, the temperature difference between the interior and exterior of the greenhouse decreased exponentially as the area ratio of roof ventilator opening to floor is increased. This means that the temperature difference between greenhouse interior and exterior decreased quickly, with an increase in the ratio of opening area when it was less than 40 to 50%, while the effect of increased ratio of opening area was less important when greater ratio of opening area was used. Here we need to make a decision when we are designing and installing roof vents on naturally ventilated greenhouses. Increasing the area ratio of roof ventilator to opening to floor area does not really significantly affect the temperature rise or the temperature difference between inside and outside the greenhouse. So a cost factor must be considered and a proper ratio must be selected. The area of side openings per greenhouse floor area decreases as the width of a greenhouse increases. This is usually the case with large-sized greenhouses. Therefore, the roof ventilators are more important with large-sized greenhouses, especially the increase in the area of roof ventilator openings. In theory, the natural ventilation rate varies linearly with external wind velocity and area of ventilation openings, while it also varies linearly with the square roots of height of openings and temperature rise. For the design purpose, wider openings are effective in increasing the ventilation rate. As a rule of thumb, minimum ventilation opening area without the use of insect screens with naturally ventilated greenhouses are 30 to 35%. More roof opening area to floor area means closer to outside conditions inside the greenhouse. Roof vents or higher side vents are needed for hot and humid air to escape from the greenhouse space, and the taller greenhouses will definitely help increase the chimney effect, contributing to improved natural ventilation rates in the greenhouse system. Insect screens are commonly used with naturally ventilated greenhouses. They help to reduce insect migration, and they also reduce crop damage. However, insect screens can reduce ventilation significantly due to resistance to airflow, and they also increase internal air temperatures. The insect screens can clog due to dust accumulation, and because of this, increasing the ratio of opening to floor area is desirable. The research shows that the insect screens in vent openings may cause reduction on greenhouse ventilation rate at about 30 to 35% depending on ventilation configuration and design. and combined use of roof and side vents are recommended with the use of insect screens with naturally ventilated greenhouses. Under highly dynamic outside climatic conditions, the best way is to use butterfly vents where one of each side of the roof vent can be automatically opened or closed or controlled depending on the wind direction. So the butterfly vents can add flexibility to control of natural ventilation process in the greenhouse. We can create an improved pressure gradient on the roof vent, contributing to improved ventilation process. Mechanical ventilation systems using pad and fan can be very effective way of cooling a greenhouse system in various climatic locations. And these systems can efficiently actually work in arid and semi-arid regions because excessive heat loads are experienced most of the year, and this requires significant cooling capabilities. As you can see on this graph, using the average solar radiation and average daily air temperature for the location, in this case Tucson, Arizona, which is located in a semi-arid climate, you can see that we have to use mechanical ventilation with evaporative cooling for the majority of the year to maintain desired climate in the greenhouse for plant productivity. However, if you look at the line or the region between the red and blue lines here, we can see that we can take advantage of natural ventilation to maintain greenhouse climate for certain time of the year. As you will remember from our discussions in the previous slides, mechanical ventilation systems require electric energy as for the exhaust fan operation and water pump operation for evaporative cooling. They also demand a large amount of water being used for the cooling process. So therefore, we can take advantage of natural ventilation systems in order to reduce the resource use in the greenhouse for cooling process. And this may be significant savings in terms of resource use, especially in arid and semi-arid regions where these resources are precious. You can also create similar graphs for other regions in the world. In temperate climates, in mild climates, you will observe that there are even more potentials for naturally ventilated greenhouse systems, and these systems can maybe the only alternative or way to cool a greenhouse system in a cost-effective and efficient way in those climates. Sometimes natural ventilation systems may not be enough to cool the greenhouse, especially in arid and semi-arid regions, just using the side vents and roof vents to achieve the natural ventilation and cooling process. In that case, high pressure fogging systems are also used to improve the cooling efficiency in the greenhouse systems, because the uniformity of air temperatures within the greenhouse using a fog system with distributed nozzles are significantly improved compared to the pad and fan system. And it is also possible to achieve water and energy savings with the use of natural ventilation integrated with high pressure fogging systems. The fog system for evaporative cooling is similar to traditional misting system in many aspects. However, the high pressure fogging system operates at a much higher pressure range, for instance 7 to 14 megapascal, or in other words 1000 to 2000 pounds per square inch, and with very low volume nozzles. The low volume high pressure fog consists of very small water droplets, in the range of 3 to 10 micron sizes, which can improve the cooling efficiency because these droplets can evaporate quickly into the greenhouse environment. Therefore, the increased surface area to volume ratio improves the rate of vaporization and ultimately the cooling efficiency. If designed, installed properly, and with proper control strategy use, no water droplets will contact the crop or floor of the greenhouse below, which sometimes a concern with the use of high pressure fogging systems within naturally ventilated greenhouses. High quality water filtration systems are also extremely important to reduce the problem of clogging nozzles with the use of high pressure fogging systems. Proper ventilation performance is critical for greenhouses in both humid winter climates and also in hot summer conditions. Due to several advantages such as low maintenance, low operational cost, and less noise, natural ventilation is usually the only air renewal process used in protected agriculture in various climatic zones around the world. There are so many designs with naturally ventilated greenhouses. As you can see on this slide, there are Venlo type greenhouse designs, naturally ventilated greenhouses with roof vents. The roof halves hinged at the ridge in this design. For instance, open roof greenhouses, the roofs hinged at the gutters, and roll up roof coverings with this naturally ventilated greenhouse design. Another type could be roofs hinged at one gutter and at the ridge, and also roll up side vents, as you can see in this greenhouse design. But there are other types of greenhouses with naturally ventilated designs and configurations. The control of airflow with natural ventilation can be limited because of the dynamic nature of the outside climate around the greenhouse. Therefore, it is necessary to analyze natural ventilation in detail and properly in order to increase ventilation efficiency for any given greenhouse design and ventilation configurations. The phenomenon of natural ventilation is complex, and its design is more difficult than fan ventilation. Methods used to evaluate natural ventilation are heat and energy balance studies. There are also other alternative methods used to analyze natural ventilation, such as wind tunnel experiments, tracer gas techniques. As you can imagine, these methods can be very time-consuming and expensive to analyze various designs and scenarios. On the other hand, computational fluid dynamics, usually abbreviated as CFD, is a branch of fluid mechanics that uses numerical methods and algorithms to solve and analyze problems which involves fluid flows. Analyzing the effects of various factors for greenhouse aerodynamics is more practical, cost and time effective with the use of CFD analysis. So because of that, past decade or so, the researchers have used CFD widely as an effective design and engineering tool to evaluate greenhouse aerodynamics, including effect of greenhouse designs, ventilator opening configurations, crop existence, external wind velocities, and wind directions. This is a typical general structure of a CFD model evaluating greenhouse aerodynamics. The modeling effort starts with creating the geometry for the greenhouse system, including the greenhouse structure, the vent configurations, crops inside the greenhouse, or other system components which should be included for the analysis. Then the whole domain, the problem domain, is discretized into finite volumes where the conservation equations are solved. The model includes a turbulence model, for instance, to characterize the turbulence nature of the flow, we can include radiation and solar load models to characterize the solar radiation in the problem. A porous medium model approach is used to characterize the crop existence in the greenhouse domain to evaluate the resistance of the crop canopy against the airflow. We can also use species transport model and discrete phase models, for instance, to evaluate evaporative cooling, for instance, high pressure fogging system use for greenhouse cooling, or if we are interested in analyzing gas concentrations inside the greenhouse system. We can also use user-defined functions, external functions, to characterize special processes, specific processes, for instance, including evapotranspiration from the crop canopy, which also contributes to the greenhouse cooling and the microclimate inside the greenhouse. Then, once all the models are included, the computations are computed, then we can achieve results and look at the details of the airflow and distribution of certain key variables in the greenhouse system to analyze the design and improve and make suggestions for the greenhouse aerodynamics. Here is an example of the result obtained from a computational fluid dynamics analysis of greenhouse microclimate. In this example, we are able to see the details of the airflow characteristics as well as the distribution of vapor pressure deficit, which is a combined effect of air temperature and humidity for the greenhouse system. In this example of CFD model, what we are looking at the result of using a fogging nozzle high pressure fogging system at the center of the greenhouse at a given height, in this case 1 meter, versus nozzles located on the side of the greenhouse at two different heights, in this case 1 meter and in this case 0.5 meter above the crop canopy. So what is best about the CFD analysis, as you can see here, we are able to look into the details of each individual variable and the uniformity distributions to make better decisions to improve the greenhouse designs and make suggestions for the growers in terms of control strategies, or make suggestions for the manufacturers of naturally ventilated greenhouse systems or cooling systems. If you would like to learn more about natural ventilation in greenhouse systems, here are some of the additional references that are recommended for you. For instance, Greenhouse Climate Control and Integrated Approach, Greenhouse Technology and Management, and Greenhouses, Advanced Technology for Protected Horticulture. Thank you very much for listening.